All right, so you guys ready for these puzzles? And so let's try something a little bit different today. Here's how we do these. I'll throw the question at you guys. I'll have you guys solve it. I'll solve it on a separate piece of paper, and then go back and see if you guys got the answer. So first question, rate the torques of the 5 doors shown from least to greatest. All the forces are the same. Do you guys see a door hinge on the left? Okay, so I see a door hinge. Okay. Ooh, I see all these arrow vectors. The torques at some kind of force. Right. And so you guys rate the torques. I'll rate the torques. You guys write these down. So from least to greatest. From least to greatest. Oh, I meant to show you guys this hint. You guys been spending the last couple of days doing a torque lab. So you guys remember torque is R cross F, right? Radial arm crossed with the force. You guys can use that right there, right? So this R crossed with this F, which really means you care about the perpendicular components. This one here. Yeah. Right. Back here, zoom in. All right. Do you have all those rates? You guys got all this? Okay. So one of those I think has exactly 0 torque. Which one has 0 torque?
E.
Yeah, E. Yeah, E. Right? Because this force is parallel to the door. That's never going to turn the door, right? Right. And actually, there's another option that's really close to 0 torque, which is which one?
D.
Yeah, D. Right. Now there's a tiny radial arm here, but this is like if I go up to the door and I push right close to the hinges. I mean, maybe with a huge force I could open the door, but it'd be really hard to, right? So I'm thinking E is like 0 torque exactly. D is next up because it's just a little bit. Which one do you think is next? C. I'm thinking C also. Now, do you guys see C and B have the same force applied to the same location? So why is C less than B? Good, right? It's at an angle. So only the perpendicular component actually does any torque, right? If it's a 45-degree angle, sine of 45 degrees is like 71%. Right? Yeah. Okay, so then C, then B, and then A would be the most torque, wouldn't it? Right? Because you get the full force, the full radial arm, 90 degrees. Okay, so right. So did you guys rank them like that? E is the smallest, and then A is the most. Goes in that order.
It's already in order.
Yeah, you're right. It is in order, right? EDCBA, just like that. 61. 2 gears are in contact and rotating. One is larger than the other. Let's show here. Compare their angular velocities and also the linear velocities of the teeth that are in contact. So angular velocity, that's how fast something is rotating. Do you guys remember the physics variable for that?
No.
It's a Greek letter omega, looks like a curly W, right? That's how fast something's rotating. And then linear velocity is like if I pick a single point and say, if I point a radar gun at that point, like a linear speed, right? Okay, so now that's back to V. So go ahead and do that. Here, I'll write something on my paper. You guys see if you can figure out something for number 61. Okay, angular velocity and linear velocity. I better name these gears, so let me help you guys out a little bit. I'm gonna call the big one gear A, and I'll call the small one gear B. Okay, got some teeth on these guys. All right, gear A, gear B. What happens if you compare the angular velocity of gear A to the angular velocity of gear B? What happens if you compare, say, like this point here to this point here? The linear speed of a tooth of gear A and the linear speed of a tooth of gear B. I think way in the day I had you guys construct some kind of gear system with some paper. You guys do that? I think, yeah. All right. So you guys did that one. All right. So you kind of have that model in your head, just different size gears. Hey, what if I put my hand on gear A and I turn it around once, do one revolution? What happens to gear B? Does it also do one revolution?
No.
Does
There's several.
yeah, there you go. Like more than one. Two's good, right? If this is a 2-to-1 ratio in terms of the radius, right? Yeah, then it would be 2, wouldn't it? Right. So just divide by time. Which one of these is greater, omega A or omega B?
B.
Yeah, B. You're right. So it should be like that, right? Right. Okay. How about the linear speed of the T? If I do the linear speed, what's it?
They should be the same.
Yeah, you're right. You're right. They are the same. Yeah, they are the same. The linear speed is the same. Right? And do you guys remember the connection between omega and V? It's this right here, right? Just multiply or divide by R depending on which way you're going. Guys remember that? Okay. So I'm gonna go. The fact that these are the same. Could I say omega A R A is equal to omega B R B? Right? Because these are the same. Therefore, these are the same. Different radial sizes, different omegas. Okay. You guys can see all that, right? Okay. Number 62, videotape. When a videotape is rewound, why does it wind up fastest toward the end? Okay, I think you guys can figure this out. I thought it was an interesting question, so I threw it on here, but I'll just go ahead and go over this with you guys. Okay, so suppose you got either an old VHS tape or an old cassette if you're doing a music version of this. Same idea. Okay.
Because the radius is much smaller, right?
Yeah, the radial size changes. Yeah. So let's say you played this whole thing and it gets to the end and got a little tape here and then a bunch of tape here, like this. It spirals around like, I don't know, thousands of times, right? Something. Okay. And then you start rewinding it. So this gear starts to turn, right? So, right, and then the tape starts to wind the other way. Right? Now, when this makes one revolution at the beginning, that only moves about this much tape, right? Just a little bit. Okay? But then by the time it gets to the end, right now there's the whole thing rewound. Right? If this makes one revolution now, whoa, look at that, like look at that huge circumference. Compared to this is a tiny circumference, this is a huge circumference. So one revolution is a completely different amount of tape moved. Okay? That makes me think of this top equation right here, x equal to theta r. Right? So one revolution for each one, different radial sizes, different amounts of tape that are pulled back. All right. 74. 74. This one, I thought this would be real straightforward, but students have been struggling with this today. No, this goes back a few weeks. We've covered this, so I want to see if you guys can get this one. We got a steering wheel. It's 22 centimeters radius, and we're going to turn this thing 128 degrees. And the question here is, how far does a point on the edge move? Say like in centimeters. How far does a point on the edge move in centimeters? So I'll solve this off screen. You guys solve that on paper.
Feels like a circumference.
Yeah, it's related to that. Yeah, yeah. You think of a couple ways to solve it. So you guys solve it, I'll solve it, and see if you guys get the answer that I get.
They're the same numbers.
I'll give you guys sort of a hint. One way to solve it, the kind of standard way to solve it, if you're applying equations, is if you're applying equations that have angles in them, in physics, do you want to use degrees, revolutions, or radians? Radians is the optimal way to go, right? Can you guys convert degrees to radians? That would be a good step to do, right? Good middle step. Oh yeah.
I think I might know the answer. If that's okay for me to say now.
Yeah. What you got?
I might be wrong. 49.1.
That sounds right. That sounds right. Okay. So I'm gonna finish solving it here. Give everybody else time to catch up. Yeah, that does sound right though. All right, how many guys got 49 centimeters? Just like, okay, yeah, all right. Let's see a bunch of guys got 49 centimeters. Awesome, awesome. I think you guys are doing the best of my classes all day. All right, this is awesome. All right, so here's one way to solve. I'll show you guys two different ways to solve it. Right, so you may have done this. You may have said, okay, I got degrees. I'm going to convert that into radians and say 128 degrees is 2.2 radians. Okay, so you got that. Okay. And then you have to do this. Okay. If you want to know how far have you turned, sorry, how far you've moved, you say how far is the turntable turn times your radial distance from the center. Okay, here, I'll give you guys a visual real fast. You guys remember this right here, right? So if you're kind of close to the center, you're not moving that far for one rotation. But if you're way out here, woo, you move the long distance, right? And that's proportional to the radial size, right? So let's break that out. Got it right there, right? But if you use this, you have to plug in radians. That's why we did radians first. 22 centimeters, bam, you got 49 centimeters, 49 centimeters. Okay, that's one way to do it. Right. I'll show you guys another way to do it. You could have said that you could have solved for the circumference first and then said this 128 degrees is proportional to some fraction of the circumference. So I got the circumference of the wheel is 138 centimeters. Right, circumference equals 2 pi r. Okay, to get that. And then you can say the amount that the wheels turn is, it's like this fraction, 128 degrees compared to the whole thing, 360 degrees. Okay, multiply that by the whole entire circumference, you still get the same thing. Okay, so you got, there's two different ways to get the answer. Right, number 75, propeller. A propeller spins at 1880 revolutions per minute. Now, even before you see the question, actually, the question is convert to radians per second. So yeah, let's do that first. Okay, can you guys convert to radians per second? I'll do it off screen. You guys do it. See if we get the same thing.
Whoa. Wait, it's Wait, what?
Anybody solve question today? Anybody got it? Right, what'd you guys get?
196.87.
That sounds right. Sounds right. All right. So, okay, well, here, show you guys here. Okay. So I did dimensional analysis, took 1880 revolutions per minute. Said, well, I want radians per second, right? So I got to do two conversions. Got to convert revolutions into radians and minutes into seconds. So you guys know there are 2 pi radians and 1 revolution, right? Kind of like circumference equals 2 pi r. That's related idea. Okay. And then there are 60 seconds in a minute. Okay. So the way to set this up, revolutions goes away, minutes goes away, and you're left with radians per second. Exactly what you're looking for. So multiply across the top, divide by 60, bam, 197 radians per second, just like that. Next question. Question B. What is the angular displacement in 2.5 seconds? So angular displacement in 2.5 seconds. you guys remember linear displacement is equal to velocity times time? Okay. What's the rotational equivalent of this?
Angular speed, velocity, times time.
Yeah, just like that, right? So how far it's turned is equal to how fast it's rotating times how much time, right? Same idea, just this is linear, this is rotational. Okay. So, oh, look, you know how fast it's rotating, right? It's not that. Put that in right there. 197 radians per second. They said for what? 2.5 seconds? Not that many radians? Hey, how many revolutions is that? How many revolutions is that?
Oh, we're doing. I thought we were doing it in radians. I just wrote down for.
Yeah, it could be that many radians, right?
Yeah. So. Yeah. Okay.
Now, when you type this in your calculator, here, so let me type this in wrong. I'm gonna type it in wrong. You guys tell me what's wrong. 492 divided by 2 pi is 776. Okay, there's something that's wrong about that. What? How did I type that wrong? Yeah. Ah, exactly. The way this calculator interprets what I typed, it said 492 divided by 2, and it stops dividing. It turns wrong, multiplies by pi. So fix that, scroll up, scroll over, insert a parenthesis. Then I need to group the 2 pi together. All right, and that's the right answer. 78.3 revolutions. Same thing. Okay. Right, you guys see that? 76. The propeller in the previous problem slows from this many revolutions per minute to this many revolutions per minute. Zoom in so you guys can see that. Okay. From 475 to 187 revolutions per minute, it does that all in 4 seconds. What is the angular acceleration? To give you guys some hints, then I'll let you guys solve this. Okay. So if you're applying these two equations, you don't want to do revolutions per minute. You want to do what per what? Radians per second. So can you guys convert these before you start using any equations? Right. So you guys are going to convert these first. Then notice the 3 numbers they gave you. It's like angular velocity, time. Hey, that's 3 kinematic values, isn't it?
Yeah.
Huh. Are you guys looking at that yellow poster hanging from my ceiling that looks like this right here? Right? If you have 3 kinematic values, you can solve for anything else.
Second equation is well.
I think so, right? Right. So you guys go ahead and solve it. Anybody got the answer? Let's get.
I think I got 2.389 radians per second. Is that right?
This is gonna be. So somebody get a negative number, right? Because it's slowing down.
Oh, if I did that for minute negative, would I be?
That's bigger.
Negative 452.
It still sounds kind of big.
Let me try this.
Here, I'll show you the beginning part of this.
I think if I did it in a different order, I could.
Is it
Oh, yeah.
like negative 7.1?
Yeah, Maya got it. Yeah. All right, so here we go. Oh man. All right, here. And so they gave you a couple of angular velocities. Okay. And you need to convert those to radians per second. So 2 pi radians in 1 revolution. 1 minute, 60 seconds. That gives you radians per second. Do that for each one, and you get these radians per second. So it started moving this fast. So it's spinning this fast. And it's spinning this fast. So it's like slowing down. Okay. Should give you guys a visual for this. Okay. Want to see a turntable slow? Slow to stop. Okay. So it's like slowing down, right? Now this one they don't have slow all the way to a stop, but it slows like that. They also told you, time is 4 seconds, so you can just straight up use that number. You have 3 kinematic values. Which kinematic formula did you guys use, first, second, or third?
Second,
Yeah, I definitely like the second one too, because bam, bam, bam. You know those 3, you're solving for this one. Right? Now later on, we can solve for theta. Actually, that's the next thing we're gonna do, but before we do that, let's get alpha first. What's the rate of slowing down? So got this. Solve for alpha. Just plug these values in. Bam, bam, bam. Bam, bam, bam. Okay. Do a little bit of algebra. Yeah, you get negative 7.5 something radians per second squared. Just like that.
I did that in my.
No, what's that? Wait. No, what?
Are you talking about the alpha?
Yeah, alpha. Yeah, solve for alpha, right?
Yeah.
I'm getting that. I think I did something.
Pause this here. All right, so you guys got that? Got that in your notes now? That's right now on paper. Right, so I've got my own follow-up question. I want to know how far did that turntable turn during that interval? I can think of a couple of ways to solve it. I'll solve it off screen. You guys go ahead and solve it and see if you guys get what I get. How far did the turntable turn during that interval? All right, who figured it out?
I think I did it.
What'd you get?
138.9.
You also got 130. All right. So I'm seeing a bunch of guys say you got about 138, 139 radians. Okay.
Yeah.
All right. So let's go through the solution. So, actually, before I tell you guys what I wrote about this page, which one did you guys pick to solve this?
The first one.
Yeah, the first one. You also could have used, also could have used the third one.
But
Because-
the third one has square roots, so.
Right, a little bit of algebra involved with this one. So, right, because you guys at this point know all the variables, because you did a little bit of conversion to solve for these guys. You were given T, we solved for alpha already, right? And now we're doing the extension question to solve for theta. The first one's the most straightforward, and again, you could have used the third one and also done a little bit of algebra and solved it that way. So I will show you guys both those ways. All right, got. Here's using that first equation. We're gonna make the first equation. And so plug in the values, okay? And then bam, you get the answer, radians. Ooh, who can tell me how many revolutions is that equal to? How many revolutions? Yeah, 22. All right. 22 revolution. Okay, and then. And then the other way you could have done it, you could have taken that third kinematic equation or made an equation out of this, solve for this theta. Right. Oh, actually, just in terms of variables, subtract this over, divide by 2 alpha, it looks like this. Right. And then you can plug everything in. So whether you do algebra first or algebra after, let's say the algebra first here, okay, get the exact same answer. So they got 2 different ways to do it. All right, you guys good there? All right. That's as far as I've been making my other classes today, but we got a few experiments here. So let's look at number 68. So we'll do 68 and we'll call it a day. Tightrope walkers often carry long poles. So if the ends are lower than the ends down, how does the pole increase the tightrope walker stability? Center, all right. How about moment of inertia? Okay, you guys remember this thing with like the pen versus the meter stick? So you try to balance a pen in your finger, it's nearly impossible. But do you guys ever try to do I have a meter stick up here? Here, down here. Back when you guys were in the lab area, you guys take a meter stick, try to balance this on your finger? Because that's a lot easier to do, right? All right, so that's probably the main reason. I think they're looking for something else. All right, we will call that a wrap on today.